Engineering School Physics. Nanoscience. In this video of Nanoscience, we will cover following topics. Introduction to nanoscience. Important features of nanoparticles. Electrical, magnetic, optical, and other properties. Semiconductor nanoparticles. Concept of quantum size effect. Quantum dots. And their applications. Applications of nanoparticles. Making of nanomaterial. We talk about the basic start of nanoscience. A background. There's plenty of room at the bottom, was the title of the lecture, given by Nobel laureate Richard Feynman on December 29, 1959, at California Institute of Technology. This has opened up the vision to get engineering nanomaterial from atom to atom to useful nanostructured, standalone, workable material, irrespective of metal, semiconductor, or insulators. This is the beginning of bottom-up approach on record. However, the use nano-size particles is there from centuries. Nanoscience has a bright future. In just another 10 to 15 years, say by 2035 to 40, nanotechnology will impact more than $1 trillion per year in products and services. Every day, new nanoparticles are coming up, new technologies to make them and to manipulate them, and new applications you can see every week. This shows the importance of nanoscience and nanotechnology. Nanoscience and AI. Artificial intelligence. Nanotechnology is a fast-developing discipline that has the potential to transform a variety of industries, including medical, energy, electronics, and materials research. The integration of artificial intelligence, AI, into nanotechnology has created a new area of research and innovation known as AI-nanotechnology. As artificial intelligence AI is already integrated in nanotechnology, so I asked what artificial intelligence knows about it. See what they have to say. First from Grok 3, followed by Google. What is nanoscience? Grok says, nanoscience is the study of materials and phenomena at the nanoscale, typically between 1 and 100 nanometers. Note, 1 nanometer equals 10 to the power of -9 meter. At this scale, materials exhibit unique physical, chemical, and biological properties due to quantum effects and increased surface area to volume ratios. It involves understanding and manipulating atoms, molecules, and structures to develop new technologies and applications. Nanoscience combines physics, chemistry, biology, and engineering. What is nanoscience? Note what Google has to say. Nanoscience is the study of materials and structures at the nanoscale, 1 to 100 nanometers, focusing on their unique, size-dependent properties. Nanotechnology, on the other hand, is the application of nanoscience to design, produce, and utilize structures, devices, and systems by manipulating matter at the nanoscale. Currently, nanoscience and nanotechnology are rapidly developing disciplines, and their results can be exploited in many different applications, from medical pharmacology and biotechnology to electronics, semiconductors, water purification, and university research education. Nanoscience and nanotechnology. We can conclude nanotechnology is a multidisciplinary discipline that involves applied physics, materials science, colloidal science, device physics, supramolecular chemistry, mechanical engineering, and electrical engineering. Nanomaterials-based tools, products, and the quality should offer better comfort at lower costs. In the next future efforts should focus on improving the features of novel nanomaterials to make them suitable for different applications. Particularly, nanotechnological research may move towards nanotechnology development in health, cosmetics, engineering, biomedical, and environment. Currently, nanoscience and nanotechnology are rapidly developing disciplines, and their results can be exploited in many different applications, from medical pharmacology and biotechnology to electronics, semiconductors, water purification, and university research and education. Research may focus on the development of new nanomaterials from other biopolymeric materials, nanofibrous scaffolds for effluent treatment, food industries, cosmetics, hard and soft tissue, engineering applications. Nanotechnologists are rediscovering old materials, such as carbon, to improve consumer and industrial products, address critical energy needs, enhance security systems, and improve the medical field. Each type of nanomaterials displays specific properties exploitable for specific applications. Therefore, a better understanding of these properties will allow the development of new and more efficient materials. What is nano and how we define nano? The word nano is from the Greek word nanos, meaning dwarf. It is selected as a prefix used to describe, which means very, very small. In number, it means 1/1,000,000th of something, or 0.0000000001, or 10 to the power of -9. As prefix, it is being used as nanogram, nanosecond, nanometer, nanofarad. A nanometer is 10 to the power of -9 meter. Define. Nanoparticles. Nanoparticles are generally considered to be a number of atoms or molecules bonded together, such that the dimension of the bonded entity is less than 100 nanometer. Size of an atom is generally taken as 1 angstrom. 1 angstrom equals 10 to the power of minus 10 meter equals 0.1 nanometer. We define nano size: 0 dimension, 1 dimension, and 2 dimension. Nanoparticles, 0D, are generally considered with a size of between 1 to 100 nanometer in all 3 dimension. If 1 dimension, 1D, is more than 100 nanometers, it is defined as nanowire. Example: carbon nanotube. If 2 dimensions are more than 100 nanometers, it is defined as nanosurface or nanocoating. Example: graphene. To give you the idea of size, an entity with a micron in diameter, that is, 1 divided by 1,000 of a millimeter, and a nano-sized object is 1 divided by 1,000 of a micron. A dimension difficult to see and feel. For example, a human hair is about 50 to 100 microns, or micrometer, in diameter. A white blood cell is about 10 microns, and a DNA is in the order of 10 nanometers. Idea of size: centimeters 10 to the power of minus 2 meters. Flowers, leaves and bee. Idea of size: millimeters 10 to the power of minus 3 meters. Straws and ants. Idea of size: microelectronics. Nano-electronics was made successfully in 1999 at HP using nanowire, nano switch, and first-time nano-size transistor. Some more items of nano size: water molecule, antibody, DNA, red blood cell of 7 micron, bacteria cell of 10 micron. Features of nanosystems. In materials, an atom on the surface is different from an atom in the bulk, because there are different potentials on the 2 atoms, interior and on surface, that exist. This is the reason of different physical properties of materials of nano, micro or larger scale systems, and properties of nanostructures. We show you graphically how outside atoms dominates in nanoparticles. Model of a nanoparticle. Now consider as a simple case a sphere of radius r. The volume of this sphere is V equals 4/3 times pi r cubed, and the surface area is given by S equals 4 pi times r squared. The ratio of surface area SA to volume V is 1/3 times r. If r is small, the surface area would be more in ratio to volume, and we would have more atoms on the surface than inside the atom. Single atom is not a case of nanomaterial, but complex molecules may behave as nanoparticle because of multi-atoms. Now, to cover one atom by other atoms in very tightly packed case, we need 16 atoms. To cover it entirely, please note, atom on surface equals 16. And atoms inside 1. Ratio 16 is to 1. This is the case of a cluster of 17 atoms. Now to cover this cluster of 17 atoms by other atoms, in very tightly packed case, we need 64 atoms to cover it. Numbers of atoms on surface 64 and atoms inside 17. Ratio 64 is to 17 or 3.76. Cluster size of 81. Now to cover this cluster of 81 atoms, we need 144 atoms. Numbers of atoms on surface equals 144. And atoms inside 81. Ratio 144 is to 81 or 1.77. This is a model for layers of atoms. Cluster size of 225 of atoms. Model of a nanoparticle of 5 layers. Now to cover this cluster of 225 atoms, we need 256 atoms. Numbers of atoms on surface equals 225. And atoms inside 256. Ratio 256 is to 225 or 1.137. Cluster size of 481 atoms. See chart. Beyond 6 layers number of atoms. Please note, when the number of inside atoms are more than the surface atoms, hence it start behaving like bulk material. Size-dependent features of nanosystems. This reveals that, as the size of the particle decreases, the number of atoms on the surface is in a greater proportion of the total number of atoms. Hence, as the particle size becomes smaller and smaller, the surface atoms start dominating the properties of the whole material. Nanoparticles have a very high surface area to volume ratio. This provides a tremendous driving force for diffusion. At elevated temperatures, sintering can take place. At lower temperatures, over shorter time scales than for larger particles. Features of nanosystems. Size-dependent properties are observed, such as 1. Quantum confinement in semiconductor particles. 2. Surface plasmon resonance in some metal particles, and 3. Superparamagnetism in magnetic nanomaterials. Magic numbers. refer to specific numbers of atoms in a clusters or nanoparticles that exhibit enhanced stability and unique properties. In lead-PB, the data show that the clusters of 7 and 10 atoms are more stable than the clusters of other sizes. These numbers are referred as electronic magic numbers. The clusters can be viewed as superatoms. These magic numbers are analogous to the magic numbers in nuclear physics, where certain numbers of protons or neutrons lead to increased stability. For example, the inert gases helium has 2 protons, neon has 10, and argon has 18 protons. Stability and structure. Magic numbers correspond to stable configurations of atoms in nanoparticles, often resulting in structures that are more resistant to deformation or aggregation. Geometric relationships. These magic numbers are linked to specific geometric shapes like icosahedra and cuboctahedra, where the number of atoms corresponds to the completion of a particular layer or shell within the structure. 13, 55, 147, 309. These numbers are associated with the formation of icosahedral structures. 38, 201, 586. These numbers are related to the formation of truncated octahedra structures. Magic number of gold nanoclusters with diameters from 1 to 3.5 nanometer are shown here for your clarity. Note them carefully. Geometric structure, gold and aluminium particles, has the face-centered cubic, FCC, crystal unit cell. However, when particles are small, having diameter of 5 nanometer or less, they have different structures. For example, 3 to 5 nanometer gold particles have an icosahedral structures, that is a regular polyhedron with 20 identical equilateral triangular faces, 30 edges and 12 vertices, rather than the bulk FCC structure. The problem with aluminum atoms is they are highly reactive. If aluminum nanoparticle are exposed to air, it would immediately react with oxygen, resulting in an oxide coating of aluminium oxide Al2O3 on the surface. So it is difficult to study the aluminum nanoparticles. However, aluminum nanoparticles can be made in solution without exposure to air for further study. Buckminster fullerene C60. A nanoparticle of 60 atoms of carbon, arranged in a cage-like structure, similar to a soccer ball, consists of 26-membered carbon rings, hexagons, and 12 5-membered carbon rings, pentagons, fused together. C60, allotropes of carbon, is a stable molecule and can withstand high temperatures and pressures. Carbon C60 fullerene is a unique carbon molecule exhibiting interesting properties and potential applications in various fields. Features of nanosystems. Electronic structure. The electronic structure of nanoparticles is a fascinating field due to the quantum confinement of electrons and the large surface-to-volume ratio. This structure, influenced by size and shape, directly impacts a nanoparticle's electrical, optical, and mechanical properties, making them valuable for various applications. When atoms form a lattice, the discrete energy levels of the atoms are smudged out into energy bands. When a metal particle is reduced in size to a few hundred atoms, the density of states in the conduction band changes dramatically. Features of nanosystems. Electronic structure. The continuous density of states in the band is replaced by a set of discrete energy levels, which may have energy level spacings larger than the thermal energy kBT. Kb is Boltzmann constant. A gap opens up and changes in the electronic structure during the transition of a bulk metal to a large cluster, and then down to a small cluster of less than 15 atoms. Note here the continuous density of states versus discrete energy levels in bulk, nanosize, and atoms and molecules. In nanoparticles, the electrons are confined within a limited space, leading to discrete energy levels, rather than the continuous band structure found in bulk materials. The large surface-to-volume ratio of nanoparticles means that a significant portion of atoms are on the surface, which may have altered the electronic properties compared to the bulk materials. The small cluster is like a molecule, having discrete energy levels. Eventually, a size is reached where the surfaces of the particles are separated by distances which are in the order of de Broglie wavelengths of the electrons. In this situation, the energy levels can be modeled by the quantum mechanical treatment of a particle in a box. This is referred to as the quantum size effect. Electronic structure dictates the types of chemical bonds and binding interactions within the nanoparticle, such as metallic, ionic, covalent, or van der Waals bonding. The electronic properties of the nanoparticle surface can be tailored through surface modifications. It helps in many applications of lasers and diodes. When nanoparticles are placed in contact with other materials, interface effects can influence the electronic structure of the nanoparticle. For example, a metal nanoparticle embedded in a matrix might exhibit different electronic properties due to interactions with the surrounding material. Features of nanosystems. Now we take optical properties. In metals, as the size of the particles decreases, one starts observing oscillations of electron gas on the surface of nanoparticles. These oscillations are called surface plasmons. When nanoparticles are exposed to light or electromagnetic waves, having a wavelength comparable to the size of the nanoparticles, and the light frequency matches the surface plasmon frequency, then the surface plasmon would absorb energy. Thus, nanoparticles start exhibiting different color as their size changes, and the frequency of the surface plasmon changes with it. This frequency of the surface plasmon absorption is a function of the dielectric constant of the material, size of the particles, and also the specific geometrical shape of the particle. We will show you such effects observed in various labs while experimenting with size, shapes and pressure. Here is aspect ratio of nanorod of size 50 nanometers. Observed size and shape dependent optical properties of nanomaterials. Note the variation of shell thickness changes the colors of nano shells. Note here how percentage of gold particles in nano cages of gold of 50 nanometers. The optical properties of semiconductors. The properties of semiconductors change with the size of it in the nanoparticles range. In any semiconducting material, there is a band gap between the conduction and valence bands in the solid. The band gap in semiconductor materials like silicon is equals 1.1 electron volt. The band gap affects its electrical as well as optical properties. With size of the particle getting smaller and smaller, the band gap varies. With size of the particle, the band gap increases. When nanoparticle becomes smaller, the absorption spectrum changes and undergoes a blue shift. By blue shift, we mean that the whole spectrum shifts towards a smaller wavelength. Now we move to electrical properties. The electrical properties of the nanoparticles also changes as other properties, as compared to the bulk properties. Nanomaterials exhibit unique electrical properties that are significantly different from their bulk counterparts due to their small size and increased surface area. These properties include increased conductivity, altered dielectric behavior, and the possibility of manipulating their electrical behavior through quantum effects and surface modifications. Increased conductivity. Nanomaterials, especially metallic, and some semiconductor nanoparticles, often exhibit higher electrical conductivity compared to their bulk forms. This is because the increased surface area to volume ratio can enhance electron transport. Altered dielectric properties. The dielectric constant and dielectric loss of nanomaterials can be modified by factors like particle size, doping, and surface modifications. These changes are important for applications in capacitors and other electronic devices. Quantum effects and surface modifications. At the nanoscale, quantum effects can significantly influence electrical properties. For example, surface plasmon resonance in nanoparticles can lead to changes in optical and electrical behavior. Quantum effects, particularly quantum confinement and surface modifications, dramatically alter the electrical properties of nanomaterials. Quantum confinement leads to discrete energy levels and band gaps, impacting conductivity and potentially creating metal to semiconductor or insulator transitions. Surface modifications, such as doping or coating, can also alter the conductivity and dielectric properties. Surface modifications, like coating or functionalization, can introduce surface states, alter charge distribution, and influence electron transport, ultimately affecting electrical behavior. Several factors can influence the electrical properties of nanomaterials. Size. In nanoscale from 10 to 30 nanometer. Shape and structure. The shape and structure of a nanomaterial can also affect its electrical properties. For example, nanowires and nanotubes have different electrical transport characteristics compared to nanoparticles. Surface modifications. Surface coatings help in modifications of surface properties. Doping. Introducing dopants into the nanomaterial can change its conductivity and other electrical properties. It is common in semiconductors. In the case of semiconductors, there is an existence of a bound pair of an electron hole that is known as an exciton. When an atom at a lattice site loses an electron, the atom acquires a positive charge that is called a hole. If the hole remains localized at the lattice site, A detached negative electron remains in its vicinity. Then due to Coulomb interaction, they would form an exciton. This exciton has a particular radius. If the radius of the exciton in a material is much less than the nanodimension of the structure, then the system is said to have a weak confinement. However, if the exciton radius is much greater than the nanodimension of the structure, then the confinement is said to be strong. The exciton leaves its signature on the absorption spectra of materials in the form of strong absorption peaks near the absorption edge. This property of nanoparticles can be used in making very fast switches. The capacitance. For any solid structure, the capacitance of the structure depends on the dimension of the structure. As a rule of thumb, the capacitance decreases as the size of the particle decreases linearly. For very small dimensions, the voltage change of the particle can be measurable when even a single electron is added to it. This leads to a staircase effect in the IV current voltage characteristics of such nanoparticles. This phenomenon is known as Coulomb blockade effect and is utilized for making a single electron transistor, SET. The unique electrical properties of nanomaterials make them valuable for various applications, including nanowires and nanotubes. Can be used in transistors and other electronic devices due to their high conductivity and flexibility. Nanomaterials can be used in energy storage in batteries, supercapacitors, and fuel cells due to their enhanced conductivity and surface area. In making sensors, nanomaterials can be used to detect various signals, including chemical and electrical changes, due to their sensitivity to environmental stimuli. Biomedical applications. Nanomaterials can be used in drug delivery systems, tissue engineering, and diagnostic tools. Features of nanosystems. Magnetic properties. Magnetic properties of nanoparticles show a variety of unusual magnetic behaviors when compared with the bulk materials. Magnetic properties of nanoparticles due to surface interface effects, including symmetry breaking, electronic charge transfer, and magnetic interactions. Materials are generally classified in following three types: diamagnetic, paramagnetic, ferromagnetic. Diamagnetic materials, generally, are not magnetized. To explain it further, an atom in a magnetic field induces currents which oppose the change in magnetic flux. The induced currents have a magnetic moment, which is opposite in sign to the applied magnetic field intensity. Paramagnetic materials are magnetized. Some atoms and ions with unpaired electrons have permanent magnetic moment. In the absence of the magnetic field, these moments usually point in random directions and thus produce no net magnetization. But in a magnetic field, these moments line up in the direction of the field and produce a magnetic moment and the magnetization. Ferromagnetic materials have a net intrinsic magnetic dipole moment and get magnetized in external magnetic field. Nanoparticle of these material is of great interest, as they are different than bulk material, with added advantages of superparamagnetism. These are referred as magnetic nanoparticles. As per Weiss concept of ferromagnetic domains, a ferromagnetic material consists of a large number of small domains, which are spontaneously magnetized. Magnetization occurs when some of these are caused to align themselves more or less parallel to the applied field. The magnetization takes place either by motion of domain walls, that is, by an increase in the volume of domains, or by rotation of domains. In the strong fields, the magnetization usually changes by means of rotation of direction of magnetization. Here we show you how magnetization takes place in ferromagnetic materials. Observe the magnetization changes by rotation in the direction of field. When ferromagnetic material is reduced to micro size, the number of independent magnetic domain reduces. Frenkel and Dorfman, in 2005, were the first to predict that a particle of ferromagnetic material below a critical particle size less than 15 nanometers for the common materials would consist of a single magnetic domain, that is, a particle that is in a state of uniform magnetization at any field. Visualize here nanomagnet above critical particle size and single domain. When the size of single-domain particles further decreases below a critical diameter, the coercivity becomes zero, and such particles become superparamagnetic. Superparamagnetism is a magnetic phenomenon observed in small ferromagnetic or ferrimagnetic nanoparticles, where magnetization can randomly flip direction under the influence of temperature. These particles have zero coercivity and have no hysteresis. Nanoparticles become magnetic in the presence of an external magnet, but revert to a non-magnetic state when the external magnet is removed. Here we show you the size effect, and magnetic nanoparticles show superparamagnetism with reduction of size, and coercivity goes to zero. The magnetic coercivity is a measure of the ability of a ferromagnetic material to withstand an external magnetic field without becoming demagnetized. Iron oxide nanoparticles, such as magnetite, Fe3O4, or its oxidized form magamite, gamma, Fe2O3, are by far the most commonly employed nanoparticles for biomedical applications. Highly magnetic materials such as cobalt and nickel are susceptible to oxidation and are toxic. Magnetic properties of some other material changes when the size goes to nano range. Bulk materials such as sodium Na, potassium K, and rubidium Rb are paramagnetic, and they turn to ferromagnetic nanoparticles. Bulk material iron, cobalt, and nickel are ferromagnetic, and they turn to unique superparamagnetic nanoparticles. It is clear that small particles are more magnetic than the bulk materials. Applications of magnetic nanomaterials in biomedical applications. Magnetic nanomaterials is used in targeted drug delivery and magnetic hyperthermia. For data storage, they are used in magnetic storage devices. In sensors applications, they are used to detect various substances, such as heavy metals. In water, being very small, they are good catalyst. In various chemical reactions. Energy storage applications, such as batteries and supercapacitors. Features of nanosystems. Mechanical properties. Nanomaterials exhibit a wide range of mechanical properties that can be significantly different from their bulk material counterparts. Key properties include strength, brittleness, hardness, toughness, fatigue strength, plasticity, elasticity, ductility, rigidity, and yield stress. These properties are crucial for nanomaterial-based devices and applications. Strength. Nanomaterials exhibit enhanced strength due to their high surface area to volume ratio and unique surface interactions. Brittleness. Some nanomaterials, particularly non-metallic inorganic materials, tend to be brittle, lacking the ability to deform plastically before fracturing. Hardness. The resistance of nanomaterial to scratching is another important property. Toughness. The high ability of nanomaterial to absorb energy before fracturing, and its resistance to damage. Fatigue strength. Nanomaterials exhibit unique fatigue behavior, which is the ability to withstand repeated stress cycles. Plasticity, the capacity of a material to undergo permanent deformation under stress, is important for applications requiring flexibility or shaping. Surface stress in nanoparticles modifies its mechanical and structural properties. Elastic properties. The intrinsic elastic modulus of a nanostructured material is same as that of the bulk material until the particle size becomes very small, less than 5 nanometer. Young's modulus. Below ~20 nanometer, Young's modulus begins to decrease from its value. In conventional grain-sized materials, hardness and strength of conventional grain-size materials, grain diameter, d greater than 1 micrometer, is a function of grain size. The dependence of yield stress on grain size in metals is well established. In the conventional polycrystalline range, diameter more than 1 micrometer, yield stress sigma y, for materials with grain size d, is found to follow the Hall-Petch relation. Sigma y equals sigma 0 plus k divided by square root d, where sigma 0 the friction stress opposing dislocation motion, and k is a constant. Hall-Petch relation. Sigma y equals sigma 0 plus k divided by square root d. This indeed an approximation, and a more general formulation is to use a power expression with exponent -n, where 0.3 less than or equal to n less than or equal to 0.7. That is sigma y equals sigma 0 plus k times d to the power of -n. Most nanostructured materials are quite brittle and display reduced ductility under tension. The need for scratch, mark and/or abrasion resistance is well established in various markets, including fingernail polishes, flooring, plastic glazing, headlamp covers, and other automotive parts, transportation windows, and optical lenses, where clear scratch-resistant coatings are used. Features of nanosystems. Properties. Reactivity. Since the electronic structure of nanoparticles depend on the size of the particle, the ability of the cluster to react with other species should depend on cluster size. This has important implications for the design of catalytic agent for various difficult reactions. Now we take very important features of nanosystems. The quantum confinement. The phenomenon of quantum confinement is important in nanosystems. In quantum mechanics, we solve a problem of particle in a box, where an electron is confined to a very small space of length L, of zero potential, within a quantum well, of walls of very high potential, so it has discrete energy levels, given by En equals n squared times pi squared times h cross squared divided by 2 ml squared. It is applicable to nanosystem or nanoparticles. Quantum confinement in nanoparticles is due to its nanoscale size, especially when the particle's dimensions are comparable to the de Broglie wavelength of the particles being confined, such as electrons or holes. This confinement leads to the discretization of energy levels and the emergence of novel optical and electrical properties. How quantum confinement works. When a particle is confined within a nanoparticle, its movement is restricted, similar to a particle in a box, resulting in the quantization of the particle's energy levels, the band gap, or the energy difference between the highest occupied and lowest unoccupied energy levels increases as the particle size decreases. By adjusting the size of nanoparticle, its absorption and emission wavelengths can be tuned, leading to changes in color and other optical properties. When a bulk material, which has length, breadth, and height, is reduced to nano size, by reducing materials' third dimension height or thickness to nano size, it will become like a sheet or coating with only visible length and breadth. The electrons in the sheet are free to move in two directions, but along the direction of thickness there is a confining potential. Hence, such particles are quantum confined in one direction. It called quantum well. When a sheet of material, which has length and breadth, and its breadth is reduced to nano size, by reducing materials' two dimensions, breadth and thickness, to nano size, it will become like a wire, or human hair or sting of web, with only visible length. The electrons in the wire are free to move in only one direction, but along other two directions there will be a confining potential. Hence, in such cases the particles are quantum confined in two directions. It is referred as quantum wire. When a wire of material, which has length, and its length is reduced to nano size, it means reducing materials all three dimensions to nano size, it will become like a dot with no visible dimension. The electrons in a dot, there will be a confining potential. Hence, in such cases, the particles are quantum confined in all directions. It called quantum dot. Watch. Bulk solid to sheet, sheet to wire, and wire to dot. Quantum well. The electrons in the sheet are free to move in two directions, but along the direction of growth there is a confining potential. Hence they are quantum confined in one direction. It is expected that a particle that is present in a quantum well shows energy level formation, and thus shows properties different than the bulk. Quantum well are not standalone, but created on some known surfaces. A thin film sheet of gallium arsenide sandwiched between two sheets of aluminium gallium arsenide is an example of how a finite potential quantum well can be actually realized in such formation of quantum confined systems. The density of states represents how many electrons can be accommodated at any particular energy level. This change has been illustrated in the figure, along with density of states d, e, for different types of quantum confinements versus bulk material. Density of states d, e, versus energy levels for different types of quantum confinements. Examples of quantum confinement effects. Quantum dots, QDs, are semiconductor nanoparticles. Semiconductor nanocrystals also exhibit quantum confinement effects, resulting in changes in their band gap and other electronic properties. Metals at nanoscale can cause metals to behave as semiconductors, with the emergence of a band gap due to the discretization of energy levels. A quantum dot is a semiconductor whose excitons are confined in all three spatial dimensions. As a result, they have properties that are between those of bulk semiconductors and those of discrete molecules. Researchers have studied quantum dots in transistors, solar cells, LEDs, and diode lasers. They have also investigated quantum dots as agents for medical imaging and hope to use them as qubits. Quantum computing. Some quantum dots are commercially available in powder forms. Quantum dots. They can be of pyramid or can be disc-like, as they are shown here. Being zero-dimensional, quantum dots have a sharper density of states than higher dimensional structures. As a result, they have superior transport and optical properties and are being researched for use in diode lasers, amplifiers, and biological sensors. Diagnostic tools. STM, scanning tunneling microscopy, and AFM, atomic force microscopy, are both scanning probe microscopy techniques used to image surfaces at the nanoscale. Quantum dots have numerous applications across various fields, leveraging their unique optical and electrical properties. They are used in light-emitting diodes, LEDs, displays, and solar cells, due to their ability to emit bright, narrowband light at specific wavelengths. Note here: quantum dot size and color. of fluorescent emission with the size from 2.5 nanometers to 6 nanometer. They can be tuned to from near-infrared wavelength to visible range, from 700 to 400 nanometers, and ultraviolet light. Features of nanosystems. Quantum dot. Applications. Some common and useful. Quantum dots. Cadmium selenide semiconductor quantum dots has size-dependent emission range. Cadmium selenide quantum dots are core type 2 to 6 semiconductor materials with size-dependent optical or electronic properties, uniform size distribution and high quantum yield. Another very useful quantum dot is lead sulfide PBS semiconductor quantum dots, which has excellent optical property, suitable for forbidden bandwidth and 900 to 1600 nanometers, near-infrared emission wavelength range, through surface ligand exchange process. PBS quantum dots can be dissolved in water and exhibit good biocompatibility, thus can be widely used for bioimaging and drug delivery. Cadmium sulfide and zinc sulfide CDS ZNS core shell semiconductor quantum dots. Means inside is CDS and shell is made of ZNS, has emission range from 400 nanometers to 460 nanometers. CDS ZNS quantum dots are gradient alloyed semiconductor materials with size-dependent optical or electronic properties, uniform size distribution and high quantum yield. CDS ZNS quantum dots are coated with octadicylamine, ODA, in toluene, with the emission peaks ranging from 405 nanometers to 460 nanometers. Quantum yield greater than 75%. There are non-toxic quantum dots for medical applications. 136. 2 type of CIS, selenium, CIGS, selenium, CZTS, selenium, semiconductor quantum dots are with excellent optical property, large absorption coefficient, and stable performance. Cadmium sulfide and zinc sulfide. CDS ZNS core shell semiconductor quantum dots are with emission range from 500 nanometers to 650 nanometers, and with size-dependent optical or electronic properties, high fluorescence efficiency, low toxicity and easy cell absorb. The CDS ZNS quantum dots can be used in highly sensitive cellular imaging, drug delivery and LED. Zinc selenide. Zinc sulfide ZNS core shell semiconductor quantum dots has emission range from 400 nanometers to 440 nanometers. Indium phosphide, zinc sulfide. InP ZNS quantum dots has emission range from 500 nanometers to 800 nanometers. Due to large exciton bow radius and high emitting efficiency, indium phosphide quantum dots have similar optical properties of 2-6 type semiconductors quantum dots, with emission spectra in the visible and near-infrared wavelength range, and with reduced toxicity. Quantum computing. By applying small voltages to the leads, one can control the flow of electrons through the quantum dot and thereby make precise measurements of the spin and other properties therein. with several entangled quantum dots, or qubits, plus a way of performing operations, quantum calculations might be possible. Quantum dot lasers. In quantum dot lasers, the confinement is in all three spatial directions. Conventional laser operation requires the presence of a laser medium containing active atoms with discrete energy levels, between which the laser emission transitions take place. In the quantum dot laser, the quantum dots play the role of the active atoms. Quantum well and quantum wire lasers have been constructed that make use of laser emission transitions. These devices have conduction electrons, for which the confinement and localization in discrete energy levels takes place in 1 or 2 dimensions, respectively. Quantum dot lasers. Hybrid-type lasers have been constructed using dots in a well, such as indium arsenide, INAS quantum dots, placed in a strained indium gallium arsenide in GaAs quantum well. Another design employed what have been referred to as INAS quantum dashes, which are very short quantum wires. Photovoltaic cell devices, PVC. Quantum dots of lead selenide can produce as many as 7 excitons from one high-energy photon of sunlight, 7.8 times the bandgap energy. This boosts the maximum efficiency from 31% to 42%. Quantum dot photovoltaic would be cheaper to manufacture, as they can be made using simple chemical reactions. Light-emitting diode devices, LED, using quantum dots as light-emitting diodes to make displays and other light sources. QD-LED displays and QDW-LED. White LED. Quantum dots are valued for displays because they emit light in very specific Gaussian distributions. This can result in a display that can more accurately render the colors that the human eye can perceive. 3D TV will be made using QD-LED. Quantum dots, QD-LED, require very little power. For example, a liquid crystal display, LCD, is powered by a single fluorescent lamp that is color filtered to produce red, green, and blue pixels. Displays that intrinsically produce monochromatic light can be more efficient, since more of the light produced reaches the eye. Solar cells, photovoltaics, quantum dots can enhance light absorption and energy conversion in solar cells, potentially increasing their efficiency. LEDs and displays. Quantum dots emit bright and pure colors, making them suitable for improving the efficiency and color accuracy of LEDs and display devices. New solar panel films incorporate nanoparticles to create lightweight, flexible solar cells. Other quantum dot applications are in biology, in modern biological analysis. Various kinds of organic dyes are used. Now quantum dots can be used, as they are found to be superior, brighter as well as stable. The use of quantum dots for highly sensitive cellular imaging has seen major advances over the past decade. Here is the artist's image of quantum dot with coating layer for biomedical applications. The use of quantum dots for highly sensitive cellular imaging has seen major advances over the past decade. Another application that takes advantage of the extraordinary photostability of quantum dot probes is the real-time tracking of molecules and cells over extended periods of time. Semiconductor quantum dots have also been employed for in vitro imaging of pre-labeled cells. The ability to image single-cell migration in real time is expected to be important to several research areas, such as embryogenesis, cancer metastasis, stem cell therapeutics, and lymphocyte immunology. Nanomedicine. Scanning electron micrograph of a breast tumor treated with nanoparticles carrying the anticancer drug doxorubicin. Purple regions show dying cells, and blue regions show healthy cells. Imaging. Quantum dots act as fluorescent probes for medical imaging, enabling visualization of tissues and cells at different levels. Drug delivery. Their small size allows them to be used for targeted drug delivery, where they can deliver drugs directly to specific cells or tissues. Doctors are worried that nanoparticle, which are so small that may cross the blood-brain barriers, it a membrane which protects the brain from harmful chemicals in the brain bloodstream. Other biomedical applications include biosensors. Quantum dots can be used to detect specific molecules and substances, enabling rapid and sensitive diagnosis of diseases. Cancer therapy. Quantum dots can be used to target and destroy cancer cells, or to enhance the effectiveness of other cancer therapies. This image shows the bamboo-like structure of nitrogen-doped carbon nanotubes for the treatment of cancer. Applications of nanosystems. Quantum dot. Materials science. Quantum dots are explored for their potential in memory devices, energy storage, and other advanced materials applications. Quantum computing, quantum dots, are being investigated as qubits, the fundamental units of quantum information, for use in quantum computers. Applications of nanotechnology and applications in daily life. Nanotechnology, the manipulation of matter at the atomic and molecular level, has numerous applications in everyday life, ranging from electronics and medicine to textiles and food. It enables the creation of faster, smaller, and more powerful devices, improved materials, with enhanced properties and advancements in healthcare and other industries. Faster and more powerful computers. Nanotechnology allows for the miniaturization and increased performance of electronic components, leading to faster and more powerful computers. Improved conductivity. Nanomaterials, like carbon nanotubes, can enhance the conductivity of electronic devices, making them more efficient. Smart textiles. Nanomaterials can be used to create fabrics that are stain-resistant, water-resistant, flame-resistant, and even self-cleaning. Self-cleaning surfaces. Nanotechnology can be used to create self-cleaning surfaces, such as windows and coatings for car paint, that resist dirt and grime. Durable and lightweight materials. Nanotechnology helps create stronger, lighter, and more durable materials for various applications, such as sports equipment and furniture. Improved adhesives. Nanotechnology can be used to optimize adhesives, making them more durable and effective, even at high temperatures. Anti-graffiti coatings. Nanotechnology can be used to create anti-graffiti coatings that make it easy to remove graffiti and other markings. Sunscreen. Nanoparticles, like titanium dioxide and zinc oxide, are used in sunscreen to block harmful UV rays. Food packaging. Nanoparticles can be used to improve the safety and shelf life of food packaging. Water purification. Nanomaterials can be used to improve water filtration and purification processes. Catalysis. Nanoparticles are used in catalysis to boost chemical reactions, reducing the amount of catalyst needed, and potentially reducing pollution. Nanotechnology is used to produce self-cleaning glasses, using sunlight to remove contamination. Nowadays, many nanoparticles, in the form of powders, are available and used in the automobile industry, in the production of tennis rackets, anti-light glasses, anti-stain glass, self-cleaning windows, and solar pane. Today, the nanotechnology focus is on designing, producing, and applying structures, devices, and systems using nanoscale materials and manipulation techniques. Nanotechnology focus. Nanotechnology is a discipline that involves applied physics, materials science, colloidal science, device physics, supramolecular chemistry, mechanical engineering, and electrical engineering, nanomaterials-based tools, products, and the quality should offer better comfort at lower costs in the next future. Nanotechnology focus. Future efforts should focus on improving the features of novel nanomaterials to make them suitable for different applications. Particularly, nanotechnological research should move towards nanotechnology development in cosmetics, engineering, biomedical, and environmental industries. Nanotechnology focus. Research should focus on the development of new nanomaterials from other biopolymeric materials, nanofibrous scaffolds for effluent treatment, food industries, cosmetics, hard and soft tissue, engineering applications. Nanotechnologists are rediscovering old materials, such as carbon, to improve consumer and industrial products, address critical energy needs, enhance security systems, and improve the medical field. Each type of nanomaterials displays specific properties exploitable for specific applications. Therefore, a better understanding of these properties will allow the development of new and more efficient materials. Making of nanomaterial. The natural sources of nanomaterials are forest fire products, volcanic ash, ocean spray, radioactive decay, and weathering processes of metal or anion-containing rocks. It is thought that nanoparticles and nanostructured materials originated from meteorites generated during the Big Bang process that led to the formation of the universe and Earth. Nanodiamonds, extracted from meteorites, are considered the most abundant type of pre-solar grain. Naturally occurring nanomaterials have been intimately associated with life development on the Earth, from the first cells to humans. Nanomaterials and their derivatives have been produced and employed by humans since prehistoric times. The major advances in nanomaterials is due to characterization techniques. It is becoming possible to better assess all nanomaterial types. Erwin Muller in 1936 invented the field emission microscope, enabling near-atomic resolution imaging. Later we got more advanced and high-resolution analysis by scanning electron microscopes, atomic force microscopes, and also other molecular modeling techniques. Nanomaterials are and can be prepared using two main approaches: top-down and bottom-up methods. Top-down methods involve breaking down bulk materials into smaller sizes, while bottom-up methods involve building nanomaterials from atomic or molecular building blocks. Top-down approach. Bottom-up approach. From atoms to clusters and nanoparticles. Advantages of top-down methods: large-scale production, low cost of production, deposition on large substrates, low environment impact. Disadvantages of top-down methods: broad size distribution, varied particle size and shape, high product impurities. Advantages of bottom-up methods: narrow size distribution, allow a control of particle size and shape, suitable for lab scale and for research, allow a control of composition. Disadvantages of bottom-up methods: difficult to make large-scale production, high cost of production, require removal of byproducts. Bottom-up technique to make nanoparticle. Nanoscience and nanotechnology fields focused on manipulating matter at the nanoscale have a history that stretches back to the mid-20th century. Significant advancements occurred in nanoscience in the 1980s and 1990s. Key milestones include the invention of the scanning tunneling microscope, STM, in 1981, the discovery of fullerenes in 1985. The term nanotechnology was introduced by Norio Taniguchi in 1974, and the publication of Engines of Creation in 1986. Building brick by brick using atoms. Required tools unavailable in 1959. One breakthrough enabling technology towards bottom-up approach was demonstrated by IBM researchers in 1982. Binning and Rohrer invented the scanning tunneling microscope, STM, and won the Nobel Prize in 1986. Note here in the diagram. To obtain scanning tunneling microscope images, constant current between atoms of probe and sample is held as the tip moves across the surface, experiencing voltage drops over bumps. The atomic force microscope, AFM, was shortly after invented by Binning and Rohrer as well. It is now widely accepted that scanning probe techniques, including atomic force microscope, constitute a key enabling tool for nanotechnology. Making of nanomaterial. Top-down approach. Some top-down methods are mechanical milling and grinding. Bulk materials are physically broken down into smaller particles through grinding or ball milling. Lithography, using focused beams of light or electrons to etch or build nanostructures on surfaces. Laser ablation. A laser beam is used to ablate a material, producing a plasma that condenses into nanoparticles. Sputtering. Bombarding a solid surface with high-energy particles or ions to deposit a thin film of material. Etching. Using chemical or physical processes to selectively remove material from a surface and creating nanostructures. Electrospinning. Using an electric field to extrude fine fibers from a solution, creating nanofibers. Bottom-up approach. Some bottom-up methods are sol-gel synthesis, a wet chemical method where a liquid solution, sol, is converted into a gel, often used to synthesize metal oxide nanoparticles. Chemical vapor deposition, CVD. A gaseous precursor is deposited onto a substrate where it reacts and forms a nanomaterial. Hydrothermal synthesis. Precursors are dissolved in water and heated in a sealed vessel, leading to the formation of nanomaterials. Biological methods. Using microorganisms, plant extracts, or DNA templates to synthesize nanomaterials. Co-precipitation. A method where two or more precursors are dissolved in a solution and then precipitated together to form a nanomaterial. Pulsed wire discharge. Using a pulsating current to evaporate a metal wire and then condense the vapor into nanoparticles. Making of nanomaterial. Hybrid approach. Lithography is a fabricating process of one-dimension and two-dimension nanostructures by replicating patterns using positive or negative masks over a substrate using photolithography, electron beam lithography, focused ion beam, soft lithography, neutral atomic beam lithography, nanoimprint lithography, and others. It is mainly considered a hybrid approach, where etching is the top-down method, and ion growth layering is the bottom-up approach. Colloidal synthesis of CDSE, where trioctylphosphine, TOP, trioctylphosphine oxide, TOPO. That cadmium compound is heated to 320 degrees Celsius and dissolves in an organic solvent at room temperature. Selenium compound dissolved in a different organic solvent is injected into the reaction vessel, causing supersaturation of the resultant CDSE solution as the temperature drops to around 290 degrees Celsius. The nucleation of new crystals stops, and existing crystals grow after a period of growth, the length of which determines the size of the quantum dots. The solution is cooled to 220 degrees Celsius, stopping the growth. A small amount of zinc sulfide is injected into the reaction vessel to coat the quantum dots and prevent them from reacting with the environment. Laser ablation. In solution, a laser beam is used to ablate a metal immersed in a solution, producing nanoparticles. Nanomaterial production using different synthesis techniques. A. Inert gas synthesis of metal nanoparticles from thermal evaporation of a metal substrate in the presence of the inert gas, and then nanoparticles condensation on a cold substrate. Nanomaterial production using different synthesis techniques. B. Thermal plasma synthesis of nanoparticles using different plasma phase chemical reactions as bottom-up approaches. Nanomaterial production using different synthesis techniques. C. Emulsion polymerization of monomers in water in the presence of an imitator and a surfactant. D. Solid phase synthesis of core-shell noble metal Fe3O4 nanostructures. For further reading, refer to following review article. Thank you very much for watching this video. We hope we have provided some insight of nanoscience and technology. You may send your comments. Please follow us by subscribing this YouTube channel and continue to watch other videos on maths and science.